Okay, so the first video for chapter 4 is going to be about the kinematic quantities in 2 and 3 dimensions. So if you remember, we've talked about one-dimensional motion, so we know how to deal with things moving in a line. We've talked about vectors, which is how we're going to deal with 2 and 3-dimensional motion. So now we're going to get into the specifics of how we do kinematics, or how things move in 2 and 3 dimensions. So first off, position. So remember, position, we need to define where things are. So we're going to use a vector to indicate the position of an object. So, and this is known, the position vector is usually denoted as vector r. So r is our position vector. So for example, in the little figure on the right, you see here, so this is if our object is at point P1, well, we have some coordinate axis, so x-axis, y-axis, and an origin. So the position vector, we're going to denote r1. So it points from the origin to the location of the object. So in component form, again, assuming this is in 3 dimensions, we can write this as vector r is, has some x coordinate in the I hat or x direction, y coordinate in the j hat or y direction, and z coordinate in the k hat direction. Now, so of course, in general, so that's where things are, but we also need to know how things move, right? So it starts off at one position P1, ends up at some other position P2. So remember, a change in position we define as a displacement. So displacement is delta r, or change in position. And remember, so this is defined as r2, or the position vector at position 2, minus the position vector at position 1. So, and you'll also see this as, instead of 1s and 2s, as finals and initials. So for example, sometimes you see finals with an F, sometimes it's just the R with no subscript, sometimes you see initials with a little I subscript, and sometimes it's a 0. They all mean the same thing. And again, in component form, right, so our displacement, delta R vector, is the displacement in x times I hat plus the displacement in y times j hat plus the displacement in z times k hat. Okay, so now that we have displacement, we can define velocity. So first off, remember average velocity. So average velocity is just the displacement over the time interval. So we take our displacement delta r and divide that by the time it took to move from the initial to the final position. And again, we can do that in terms of components. So we have the average velocity in the x direction times I hat, plus average velocity in the y component times j hat, plus average velocity in the z direction times k hat. Okay, so now our instantaneous velocity, well again, remember this is the same thing we did for one-dimensional motion. We imagine taking this delta t time interval and shrinking it so it's smaller and smaller and smaller and smaller and smaller and smaller and smaller. And remember, that's just a limit as delta t goes to 0, and then that just becomes a derivative. So the instantaneous velocity is the derivative of the position with respect to time. So dr dt. And again, we can write that in terms of the components. So in terms of the components, right, so if we have x as a function of time, y as a function of time, z as a function of time, we take dx dt, and that's our x, or I hat component. dy dt is our y, or j hat component, and dz dt is the k hat component. And again, equivalent to this, we can also think of this, so the dx dt corresponds to our the x component of our instantaneous velocity. So that's v sub x, and v sub y, and v sub z. So, and again, acceleration works exactly the same way, except once again we have we're going to do all the different components. So for average acceleration, we take change in velocity over time, so delta v over delta t. And again, we can do that component by component. So we find the change in the x component of the velocity over the time, change in the y component of the velocity over time, and change in z component of the velocity over time. Or again, we can write this in terms of the x, y, and z components of the average velocity. And then to get to instantaneous velocity, just like we did for instantaneous acceleration, just like we did for instantaneous velocity, we imagine taking that time interval and shrinking it smaller and smaller and smaller and smaller and smaller. So we take the limit as delta t goes to 0, and once again, that corresponds to a derivative. So instantaneous acceleration is the derivative of the velocity with respect to time. So dv dt. And again, we can write this in component form. So we take the derivative of the x component of the velocity with respect to time. That gives us our I hat component. dvy dt gives us our y or j hat component. And the derivative of the z component of the velocity with respect to time gives us our z or k hat component. And again, if you prefer, we can write this as a sub x, a sub y, and a sub z. And again, remember, since the velocities are the derivative with respect to position of the time, so if we take one derivative gives us, so if we start off with our position as a function of time, first derivative gives us the velocity, we take another derivative with respect to time, that gives us the acceleration. So we can also write the acceleration in terms of these second derivatives. So either way, so all of these different descriptions of the acceleration are exactly the same, just written in slightly different ways.